We shall now be considering some other sample problems for Module 2, the Rankine's active pressure. So we have here the first problem. A frictionless retaining wall is shown in the following figure. We are to determine, letter A, the active force or piece of A after the tensile crack occurs, and letter B, the passive force or that is designated as piece of B. So first, we take a look at the figure presented. We have here your retaining wall, which is 4 meters high, and then we have here the properties of the soil. So the unit weight of the soil is given to be 15 kilonewton per cubic meter. The angle of friction is 26 degrees, and the cohesion is 8 kilonewton per meter squared. So this is a cohesive soil. And we also notice that there is the presence of a surcharge load, which is equal to 10 kilonewton per meter squared. So we are to determine the active force, the piece of A, and the passive force, which is the piece of we first begin with the active force after the tensile crack occurs. So first things first, we have to solve first for the value of the coefficient of Rankine's active earth pressure, designated as a case of A. And we said that we can solve that through the following equation. Tangent squared multiplied by the quantity 45 minus the angle of friction divided by 2. And since the angle of friction is given, we can directly substitute this equation, and we come up with the value of our coefficient of Rankine's active earth pressure, that is 0.39. Next is we will now be solving for the value of the active earth pressure, designated as sigma prime of A. So we shall be presenting the solution in a tabulated form. And on the first column, we have the Z, or the depth, and this is in meters. The second column is for the vertical effective stress. The third column is for the coefficient of the active earth pressure. And then for the last column is for the active earth pressure. So at Z is equal to 0, basically it's supposed to be 0, but notice that we have the presence of a surcharge load. So the introduction of this surcharge load will add a vertical stress at Z is equal to 0. So that becomes now our vertical effective stress, and that is 10 kilonewton per meter squared. Next is at a depth of 4 meters. At a depth of 4 meters, we said that the vertical effective stress at this point is simply the weight of the soil it carries above. So that becomes the total effective stress at this point is the surcharge load, which is 10, plus the weight of the soil. So that becomes 15 unit weight multiplied by the distance, 15 times 4. So since there is no water, there is no presence of groundwater, we will not subtract any stress coming from the pore water. So this now becomes 70 kilonewton per square meter. And then next is the coefficient of the active earth pressure. We were able to solve this a while back, so we simply input the data, and that is 0.39. And same as at a depth of 4 meters, this is also 0.39. So this time, we can now solve for the active earth pressure, Rankine's active earth pressure. And we say that we can solve that with the following equation. That is the vertical stress, or unit weight, multiplied by the depth, multiplied by the coefficient, minus twice the cohesion, and multiplied by the square root of coefficient of active earth pressure. So substituting this equation at Z is equal to 0, that becomes now 10. So this 10 is actually this unit weight multiplied by the distance, or this vertical effective stress. So that is simply 10 times the coefficient, which is 0.39. So 10 times 0.39 minus 2 times the coefficient, which is given to be 8, So 2 times 8 kilonewton per meter squared multiplied by the square root of the coefficient, which is 0.39. So simplifying, we come up with a value of a negative 6.092 kilonewton per meter squared. Next, at z is equal to 4 at a depth of 4 meters, our active earth pressure is, again, the vertical effective stress, that is 70, times the coefficient 0.39 minus this quantity, so that is twice times 8 times the square root of 0.39, and simplifying this, we come up with a value of 17.308 kilonewton per meter squared. So after tabulating, after being able to solve the values of active earth pressure, we can now plot the diagram. So below is the diagram, the pressure diagram for the active earth pressure. So at z is equal to 0, the value is negative 6.092. So at z is equal to 0, we go to the left side since it's negative, and this is negative 6.09. So there is a little discrepancy. It's because I used 3 decimals in the calculation. And then next, at z is equal to 4 meters, the value is 17.308. So from here, at z is equal to 4 meters, this is now 17.308. So from our diagram, we can solve for the value of this one, the depth of the tensile crack, and by ratio and proportion, that is 6.092. This value is to z is equal to this value 17.308 is to this distance. So this distance is 4 minus the value of z on this particular depth. So remember that we have a total height of 4, and this distance is designated as z. So substituting, we now come up with the value of z, which is 1.041 meters. So this one. So since the required is to find the active force after the tensile crack, we will only be considering this part of the diagram. So this is the point wherein it's a representation of where the tensile crack occurs. And after the tensile crack, we will only now be considering this part of the diagram. So we simply have to get, sabi natin, the active force is simply the area of the diagram. So therefore, piece of A is simply the area of this triangle. So that becomes 1/2 times the base, which is 17.308 multiplied by this height. And this height is 4 minus 1.041. So our active earth pressure is 25.607 kilonewton per meter. And this is now our answer for item A. Next, we now go to part B, which is what is the passive force. So we shall be following the same procedure. First is we have to solve for the value of the coefficient of the passive earth pressure. So P stands for passive, and that is case of P is equal to tangent squared multiplied by the quantity 45 plus the angle of friction divided by 2. So the angle of friction is given to be 26, and substituting it, we come up with a value of a coefficient of passive earth pressure to be 2.561. Then next is we solve for the next procedure is now to solve for the passive earth pressure designated as sigma prime of P. So again, we shall be presenting the solution in a tabulated form, and The effective vertical stress didn't change at all, so we will be maintaining the same values that we used from solving the active earth pressure. So next, the column 3 is the coefficient of the passive earth pressure, which we were able to solve a while back to be 2.561. And then since we already know the value of the coefficient, we can now proceed to solve for the passive earth pressure using this equation. So notice that this is the same equation we used from solving our active earth pressure. So what has changed is the sign. This was minus a while back in the active earth pressure, but in the passive it becomes plus or positive. So substituting at z is equal to 0, that becomes 10 times the coefficient of passive earth pressure plus 2 times the cohesion multiplied by the square root of the coefficient, which is 2.561. This now will yield a value of 51.215 kilonewton per meter squared. And then at z is equal to 4 meters, that becomes 70 times 2.561 plus 2 times the cohesion times the square root of the coefficient, and this will yield into a value of 204.875 kilonewton per meter squared. So since we already know the values, we can now this is now the pressure diagram for our passive earth pressure. So at z is equal to 0, the value is 51.215. And then at z is equal to 4 meters at a depth of 4 meters, the value is 204.875. So the values we were able to solve on the table. From here, we can now solve for the passive force. We have said that the passive force is simply the area of the pressure diagram. So you can view the area as either trapezoid, or you can consider first the rectangle and then plus the area of the triangle. So our passive force now becomes, first let us consider area of the rectangle, that is 51.215 times the distance or the height, which is 4 meter. And the next is we will consider the area of the triangle, that is 1/2 times the base. The base is 153.6 kilonewton per meter squared. How did we arrive at this value? That is simply 204.875 minus 51.215 times the height, which is 4 meters. So our passive force now is equal to 512.18 kilonewton per meter, and this is now our answer.